then this first slide, most of this should be reviewed from Algebra 2. A matrix is just a rectangular array of numbers in rows and columns. So this idea about rows and columns is going to be really important. When I think about work that I do with matrices, I often think about, like, if I were on a computer, if I were doing some kind of like spreadsheet program, like Excel. Because, you know, in Excel you have different rows and columns, and then in each row and column entry you have a specific thing you can put right there. That's kind of what a matrix is. Matrices have something called order. Another word for order would really be dimension. And order is m by n, where m is rows and n is columns. So that was one thing you should have done in Algebra 2, was name the order of the matrices. Order becomes important for some of our operations. Some matrices need the same order in order to perform the operation, like addition and subtraction. And then other matrices don't necessarily have to have the same order, but their columns and rows have to be equal, and that's for matrix multiplication. Okay, so order is something that we'll look into. And then finally, entries are just the numbers in the given row and column. So I could give you a matrix, and then I could say, look at the entry in the second row, third column. And everybody would know where to look, second row, third column, and we'd all see and name the same entry. So it's kind of like when you're thinking about like a spreadsheet program or an Excel, like how they name the cells, A6. Okay, so I think our first example is from the textbook, and I don't know that you necessarily have to write this down. If you want to jot it down with us, you can, but it's on page 538. It's example 1, and we're just going to do 4 different problems and name the order. So remember, order is really the dimension. It's m by n. You need to say to yourself during this chapter, row by column. That's how you name the order, row by column, row by column. So what would we say for part A, row by column? 1 by 1. That one's easy. Order, row by column. 1 row, rows are horizontal. 4 columns. 1 by 4. This has its own name. Anytime you have a single row, so a 1 by any number of columns, that's called a row matrix. If that were reversed, if that were a 4 by 1, so it had 4 rows and 1 column, we could call it a column matrix. So some matrices have special names. This dimension or order, Emily says 2 by 2. And this one is one that has a special name as well. It's called a square matrix. So square matrices will have special meaning to us in some scenarios. Some of the things that we do with matrices, like finding inverses and determinants, can only be done with square matrices. And square matrix just means the number of rows is equal to the number of columns. So 2 by 2, 3 by 3, 4 by 4, etc. And then name this with your group. That's all there is. Sorry, I can't get that over there. Elise, what do you guys say?
3 by 2.
3 by 2. Remember, rows are horizontal, there are 3 of them. Columns are vertical, there are 2 of them. Rows are horizontal, columns are vertical. Excellent. Okay, this is new to you from Algebra 2. So if you haven't seen matrices other than Algebra 2, you probably haven't necessarily talked about augmented matrices. So I would write this down and the example on this one. So an augmented matrix is a matrix derived from a system of equations. Notice that in this particular example that we're showing you, you only see a system of equations. So it looks very much like the stuff that we did in our last chapter, chapter 7, a 3-variable system. We've got x minus 4y plus 3z equals 5, negative x plus 3y minus z equals negative 3, and 2x minus 4z equals 6. And we're going to write an augmented matrix. Now the thing about the augmented matrix is you're going to take a system, and just by looking at the system, you should be able to tell what the dimensions of your matrix are going to end up being. We're going to have 3 rows, and then when I look at the different types of terms, I'm going to have a column for x, a column for y, a column for z, and an additional column for that constant on the other side of the equation. So that would be a 3 by 4. Okay, so let's write our augmented matrix together. We know it's going to be a 3 by 4 matrix, so I'm going to give myself a little bit of space to get 3 rows. And I can take that very first equation. I like my systems always to be in alphabetical order before I go into augmented matrix. That way everything's in the same spot. And I'm just going to pull the coefficients to the variables. I'm not going to put the variable in the matrix. The matrix is only going to have number entries. So the coefficient to x is 1, negative 4, 3, and then we're going to have our 5 in the first row. So 1, negative 4, 3, and these are all coefficients to the variables. To show that where our equal sign is in the matrix, we're going to put what I draw as a colon. You'll see it in the book, they'll do 3 dots vertically. That just seems a little bit excessive to me. I'm just going to do 2. I'm used to drawing colons. I'm not used to drawing 3 dots. And then I could do that for every row. So then the next equation would be negative 1, 3, negative 1, negative 3. And the last one, just be really careful if in a system you're ever missing a variable. Make sure that you put the placeholder of 0. So somebody who sees this matrix, because it has the colons there, would see it as an augmented matrix, and they could put it back together as a system. Over there on the left side before the colons, you got those 3 numbers, that's going to be the side with the variables. So you're going to say that first line is x minus 4y plus 3z, and then the colon signifies your equal sign, and must equal 5. Now, before we go on, and we're going to do a little bit more of this here in just a little bit, but I am going to just name really quickly something called a coefficient matrix, because we'll start talking about, we'll do some work with augmented matrices, but then we'll also look at just coefficient matrices. And so a coefficient matrix is just a matrix made up of the coefficients. When you look at the system, your coefficients are only on the left side of the equal sign. So the coefficient matrix would be different than the augmented matrix. It wouldn't include those constants, okay, that are equal to. So if I were going to make a coefficient matrix here, it would be a square matrix, 3 by 3. And I would leave out the equals. So we're going to see both of those, augmented matrix and coefficient matrix, as we delve deeper into chapter 8 and start solving systems of equations. Sometimes we'll use the augmented matrix, that's what we're going to start with, and then other times we'll do other methods that require just the coefficient matrix. At the end of chapter 8, you guys will have additional ways to solve systems of equations. So like think back to the last chapter, you could do elimination, you could do substitution. Technically, you could graph lines and find the point of intersection. So for your next ACT, if you take an ACT and you have a system of equations, you'll have at least 2 or 3 new ways to solve the system. So you can decide whichever one you like best. So we're going to do some of the same things we used to do, but with matrices. Okay, these examples are from your textbook, like from the same pages as your assignment. So I just put up here page 547. we're just going to practice, like, can you guys write an augmented matrix? And so if you want to write down the linear system, you can, but you could also just, like, look from the board and write the augmented matrix on your paper, and then you could name that problem so you could go and check it later. So I'm going to give you a little bit of time. See if you can write the augmented matrix there. And you can kind of look and compare, does it look the same as what I have up on the board? So really important things I'd be looking for in an augmented matrix. Do you have the colons where the equal sign is? Notice that everything to the left of the colon should represent coefficients to XYZs, XYs, XYZ, W, depending on how many variables there are. And on the right side should be only constants. See if you can work backwards. So you'll have some problems on your homework assignment like this tonight. Can you write the system of linear equations that's represented by this matrix? And it'll say in your directions, use X, Y, Z, W. Just start pulling like whatever variables you need until you don't need them anymore. So you might just use X and Y, X, Y, Z, or maybe there are four, then you need X, Y, Z, and W in that order. So can you write the system of linear equations? This is on the same page, number 23. When I'm writing the system of equations, my first column is going to be x, my second column is going to be y. There's my equal sign, so this would be x plus 2y equals 7, 2x minus 3y equals 4. We feel comfortable with this? Excellent. Now, the next things we want to talk about are, okay, so we can write these augmented matrices. What are we going to do with them? Well, we're basically going to solve those systems. We're going to find out what's X, what's Y, what's Z, what's W. Okay, we're going to solve the system. In order to do that, one method is row operations. So these are what we consider to be elementary row operations. Think about the word elementary, usually implies basic, simple, easy. These are the type of row operations you can do. And when the book talks about rows, they also call them equations. Because in the augmented matrix, every row represents one of the equations in your system. So, things you can do. Interchange two equations. For those of us who came from Mr. Griebel, and when we did three variable systems, we labeled like R1, R2, R3. Those things are going to come back to us in matrices. So an interchange of two equations, I could signal like this, R1 switch with R2. And I just have arrows going back and forth. So you're allowed to move rows up and down, switch the locations of the rows as you wish. You can also multiply by a non-zero constant, and that's called a scalar. So I could say, okay, I want to take row 1 and multiply it by 3. So I can do 3 times row 1. And then every entry in row 3 gets multiplied. And the last bullet point there is kind of a combination of that second bullet along with addition or subtraction. So you can add a multiple of an equation to another equation. You could do something as simple as R1 plus R3, or you could say I need to do 2 times R1 plus R2. So those would be examples of that third bullet. If you're doing two things at once, you're multiplying a row by something, and then you're also adding it to something else. So if you use the R1, R2, R3 previously, you're going to feel pretty comfortable. I use sub 1, sub 2, sub 3 in matrices, but if you have it like R1 on the same line, that's not going to bother me. Now, those are the row operations that you can perform, and you're going to perform row operations so that you get matrices in something called row echelon form. REF, row echelon form. And then these are 3 bullet points for what does row echelon form mean. I'll give you a chance to write those down, and then I'll show you an example of something row echelon form. Okay, so here are some things you need to know about row echelon form. If you have a row that has only zeros in it, it should be at the bottom of the matrix. That's a pretty boring row, okay, but it should be at the bottom. In all of the other rows, you can have other numbers, but the first number besides 0 in a row has to be 1. So we call that a leading 1. So you can have a row that says 0, 0, 1, 5. You can have zeros, but the first number needs to be 1, and then you can put any numbers behind it. And that would be considered row echelon form. For 2 successive rows, so a row and then another row that follows it directly, the leading 1 in the higher row has to be further left than the leading 1 in the second row, okay, or the lower row. So you're going to start to see like this diagonal of 1s coming down your matrix as the 1s get pushed back. Okay. So I'm just going to draw an example of a matrix that looks like row echelon form. That to me fits all the qualifications of row echelon form. If I have a row of zeros, it's at the bottom of the matrix. Check. And most likely you probably won't have a row full of zeros, but if it's there, it should be at the bottom. Okay. All of the other rows have their first non-zero entry as 1. So this is what I would refer to as my leading 1. And then they could be followed by other numbers, that's fine. My higher row has the 1 further to the left than the lower row. So they can't have 1s in the same position. That 1 needs to be moved over. And I could certainly have this one be 0, 0, 1, 2, or something like that. That would still qualify for row echelon form. And then you might even see, like on some of them, you have a 1 right here. Okay, that's fine. And finally, before we leave this one slide, we have one other thing that'll come in handy later. It's called reduced row echelon form, RREF. And in reduced row echelon form, there are zeros above and below every leading one. If we were working on solving a system of equations and we wanted to use reduced row echelon form, this example that I gave you previously is not in reduced row echelon form because after the 1 there's a 3 in the first row and then there's a 2 in the second row. Those would need to be zeros in order to be able to consider reduced row echelon form. Now in reduced row echelon form, if you're solving a system of equations, this last column that would be like separated by your colons, that can have other numbers besides 0. Okay. But you would just need, in this little section where your coefficients are, you would have only zeros and ones. And that'll come in handy later when we look at our calculators. Okay, reduced row echelon form. For most of the time, if we're working by hand without a calculator, I would do just row echelon form. So let's look at an example. This is example 4 from page 541. So you're going to have some problems like this on your homework tonight where they're going to give you a matrix. It could be an augmented matrix or otherwise. And they're going to give you a list of row operations that they want you to perform to get it into row echelon form. Today you get the steps. Tomorrow you have to think of the steps. Okay, so as you're working on your homework or as we're going through this example, think about like what is our goal and how are we deciding which row operations to perform. So I'm going to show you what their first set of directions is in this example, and we're going to do what they say. So the first set of directions says, add the first row to the second row. So which row is changing? Row 1 or row 2? Add the first row to the second row. The second row is changing. Okay? So what I would do when I'm doing my row operations is I would copy my matrix. It's a 3 by 4. Since I'm changing the second row, I'm going to do right here, row 1 plus row 2 in the second row. I'm actually going to go ahead and copy my first and third rows so I don't try changing them. So my first row is 1, negative 2, 3, 9. My third row is 2, negative 5, 5, 17. And I'm going to do my work for that second row. Okay, 1 plus negative 1 is 0. Negative 2 plus 3 is 1. 3 plus 0 is 3. And 9 plus negative 4 is 5. So I have added row 1 to row 2. And I now have a new second row in my matrix. Now think about why they would have said to do row 1 plus row 2. We're trying to get it in row echelon form. Our first row has a leading 1, so our first row is really good to go in row echelon form. But our second row didn't have a leading 1, and it would need a 0 right underneath that previous leading 1. Okay? So what they did was they chose to add those 2 to get that 0. And by doing that, they lucked out and they got a leading 1 right here, right? So now our second row is also good for row echelon form. We need to follow the second step to row echelon form, and they're going to provide you the steps today, but you'll come up with your own tomorrow. They tell us, add negative 2 times the first row to the third row. So which row is changing? The third row. Okay, so just try and keep track of like what are you keeping the same And what are you changing? Someone copy. 1, -2, 3, 9, 0, 1, 3, 5. These are good to go for row echelon form, so I'm going to leave them alone. But I'm going to do -2 times row 1 plus row 3. And I'd like to see you guys, like when you do your own row echelon forms, you should use the same kind of notation with R1s, R2s, R3s, so that we can kind of go back and check our work if we make a mistake. Okay, so I'm going back up to the previous matrix, the one that I had changed, the second row for. I'm going to take -2 times the first row and then add it with the third row. So -2 times 1 plus 2 gives me 0. Do you see why they did that? So they could get their 0? Okay. -2 times -2 plus -5. -1. -2 times 3 plus 5. -1. -2 times -9 plus 17. -1. You see where those numbers are coming from? You're doing 2 steps at once. You're multiplying the top row by -2, and then you're adding it with the third row. Thinking about row echelon form, which is our goal here, what do you think their next step may be? What's that? By 0? Oh, well, we can, so if you go back to your row, elementary row operations, you're allowed to multiply by a non-zero scalar. But you wouldn't want to just multiply by 0 because then you don't get any information. Everything turns into 0, right? Why would you want to multiply by 0? What was your goal? Okay, if you have a row full of zeros, it goes on the bottom, but you don't need a row full of zeros on the bottom. Okay, so my example is not like what every row echelon form looks like. So only do that if you end up with a row full of zeros. Don't try to get a row full of zeros. Yeah, what would be the goal of row 2 plus row 3? It'll get you what? A 0 in that second column, which you need. You need your leading one to be moved over, right? So we're going to do row 2 plus row 3 for our next step. And I'm going to keep my row 1. I'm going to keep my row 2. I'm going to change row 3. I'm trying to get it to be 0, 0, 1. And to go back up to the previous matrix, 0 plus 0 is 0, 1 plus -1 is 0, 3 plus -1 is 2, and 5 plus -1 is 4. Yes, there is a point. I'm going to get to it at the end when we get it in this form. All right, so I'm getting closer, right? The zeros have now shifted over. Is it row echelon form yet? No, what do we have to do to the third row? Well, you probably don't want to add or subtract with row 1 or row 2 because by adding or subtracting with row 1 and row 2, you're going to introduce numbers again. Like 1 plus 0 would be 1. So you would not have that 0, 0 look. So you're really, really close. You have 0, 0, 2. You want it to be 0, 0, 1. What could you do? Multiply by 1/2. You're not allowed to add or subtract numbers to the rows. You are allowed to multiply by a scalar, right? That's one of your elementary row operations. So let's multiply by 1/2, row 3. So row 1 stays the same, row 2 stays the same. These are good to go for row echelon form. I just need to multiply row 3 by 1/2. I'm going to get 0, 0, 1, 2. So like this looks like row echelon form. I don't have any rows of all zeros, so I don't have to worry about that. But in each row, the first non-zero number is a 1. And the higher up I am, the further left that 1 is. And then it moves over to the right, and then it moves over to the right. So that's considered row echelon form. Okay, are we feeling okay with that? Tonight, they'll tell you the steps. And so you'll get just some chance being used to row echelon forms and doing the row operations. Okay, what's the point, right? Remember, this is an augmented matrix. That means you could rewrite it as a system. What does that system look like then? X minus 2y plus 3z equals 9. Y plus 3z equals 5. Z equals 2. If I asked you to solve that system, could you do it? What would you do? Plug z in to the second equation so that you could solve for y. Okay, so I would do y plus 3 times 2 equals 5. That's y equals -1. And then you have y is -1, z is 2. Plug it into the first equation. This will be x plus 2 plus 6 equals 9. So that will be x equals 1. And you have your ordered triple. Okay. This process right here, what you're doing with that system, the book is going to refer to that as solved by back substitution. It just means like once you figure out one of the letters, and then you have an equation with 2 variables and one equation with 3 variables, you just have to back substitute. Put it into those other equations until you find all the variables. So what you really did with your row echelon form is, sorry, gotta play in the middle of the scrolly bar. You solved this equation from the very beginning. Okay, so this equation from the very beginning, x minus 2y plus 3z equals 9, negative x plus 3y equals -4, 2x minus 5y plus 5z equals 17, which, thinking about like your chapter 7 test, you would do elimination twice to eliminate a variable, then solve a 2-variable system. You could solve it that way, but now you have an additional method. Get it in row echelon form, and as long as it's in row echelon form, you'll know z, and then you can back substitute. Pretty handy. Okay. Here's your assignment. It's on your gold sheet.